Alright, well, welcome back. So hopefully that was not too bad for people. I will get these graded as soon as possible. We're not going to talk about them yet because I don't want to give any sort of unfair advantage to the other section that takes the exam tomorrow, even though they're different exams. Um, Seeing a sample exam is kind of an advantage, so. Um, and the water filter guy came during the test. That's a bummer. Timing is always tricky. Um, all right, so yeah, and if you feel like you need to talk about something from the exam before I get it graded and get feedback back to you, you can always come by office hours, and I have hours Thursday and Friday morning as usual. So, but hopefully, not a big deal for people. All right, so any questions before we start? I want to say a little bit more about PA3 and then I want to get back to talking about trees. But any questions before we get into that?
Just a really quick comment about the exam. It seemed all right to me, but that question number two on the short response, all those corrections, it was confusing me.
I may just ditch that question and give everyone credit for it because it was a little confusing. Um, and I apologize for that. The types of variables had nothing to do with the question. I put those in so that people wouldn't worry about, this is an undeclared variable. But apparently I messed that up, so sorry about that. But I may just give people credit for that because it was kind of confusing and I didn't mean it to be. All right, other questions or comments? All right, so I posted yet another version of the programming assignment with a very minor correction that I mentioned in class the other day, which is what to call your main program. So let me pull that up. So this is version 3, and this is posted on Canvas, and I've put notes in Canvas in the assignment itself around the PDF explaining what I changed from this version to the previous one. And the only change is your makefile should build an executable file named plate, not main. And that's to be consistent with what's described up here in the beginning of the assignment and the way that you run it in the startup example and the way that we've been running it in class. We've been calling it plate across the board, but I had a typo here at the very end where I said make your executable file plate. So go ahead and make it main. If you already made your make file, just change main to plate and you're good to go. There were some questions in Discord about what I needed the files to be called. Did you have to call it main.c or plate.c? Did you need your hash and list to be in separate files? And so on and so forth. So in PA 1 and 2, we spelled that out very explicitly in the assignment. I deliberately have not specified that for PA 3. I want you to figure out for yourself what makes sense. I hope that people will not write a single, file called pa3.c with 1,000 lines of code in it containing hash code and list code and a main program and prototypes and all of that stuff. I hope that you're going to partition this out into pieces for the sake of organizing your work, not having to go into a big long file every time you want to work on anything and so on. But I'm not making a requirement for this assignment for how you organize it. So you will not lose points, for how you do it. But I want you to think about what makes the most sense, and hopefully from the first two assignments you've seen some examples um, of the experience when you break things out and put things in separate files and organize things logically. And hopefully, those experiences compel you to continue to do that when you go forward, whether you're asked or not. Similarly, I did not explicitly say you need to have good commenting in here. You need to explain what your code does. You need to describe your functions. I'm hoping people will do that because it will help you writing this code. There's so many pieces to this, so many kind of moving parts, that anything you can do to keep straight what's doing what is going to help you. And the best way to do that is to use, carefully chosen names for variables and functions and stuff, and to use a lot of commenting. So the lack of, imposed structure on PA3 is an invitation to you to kind of explore what makes the most sense for you, what works for you, what helps you the most. And so I hope people will, take advantage of that and do something that that seems reasonable to them. Or just put everything in the header as someone suggested in chat, but probably not. All right, so that's the only update to PA3. Any questions about details, nuances of PA3 so far?
Sorry, what was that?
Any questions about details or nuances or how to get started and so on with PA3?
Suppose I should read that assignment.
It's a 6-page assignment and it's very dense. So if you haven't read it, and if you didn't catch it when we went through it in class on Monday, yeah, you definitely want to get into it as soon as possible, because it's got a lot of stuff.
For all the classes, so I understand.
Okay, cool. So let's just add a little bit of meat to the bones on a few of these things. So, for example, your hash table is, what's a hash table? It's an array. The hash function points to things in that array, but the hash table itself is just a plain old array indexed from 0 through some integer. And I've advised that you declare it as a hash entry star, meaning it's an array of hash entries where hash entry is itself a typedef to a struct node pointer. So this is a sentinel node to a linked list, and this is an array of sentinel nodes. So if we think about hash entry, I'll move this out of the way in a second. Hash entry star hash table. So there's our declaration of our array, right? And so hash table is a plain old array, not an associative array. And each of these things in here is a hash entry, which, if you follow the typedef, is a struct node pointer. And when you write this statement in C, you're telling the compiler this is what hash table is, right? It's an array containing hash entries, but it doesn't actually point to anywhere usable in memory yet. So you need to do this malloc business, right? And so what's a malloc statement look like? Malloc, well, how many bytes do we want to allocate? So it depends how many bytes we need for a hash entry. So you can say size of hash entry. And that's the size that you need for one hash entry. This is an array of, let's say, n hash entries. So you need to allocate n times the number of bytes you need for one entry. And you could just say something like, hash table equals that malloc. So where's the best place to do this? and the other things you need to do when you initialize your hash table. What function would you do that in? Any ideas?
That would be in hash init, right?
Yeah, that would be in hash init. That's one of the main things hash init does. So construct the initial empty hash table. So that's where you're going to do this declaration, and then do this malloc statement, and then you've got, you know, an array of hash entries, but those hash entries are probably null. So even though I've got
the assignment that you can't assume a predefined hash table size, so
right. So you're going to call hash init with an integer, which is how many entries you want in the hash table. And so I'm calling that n over here. Say again?
Doesn't that limit the size?
It fixes the size. So your main program will by default work with a hash table with 100 entries. And so it would call hash init 100. But in your main program, when you parse your command line arguments, if you see 1,000, call hash init with 1,000.
Okay, that makes sense.
Okay. And then remember, each of these is a sentinel node, and so it points to a linked list, and linked lists can grow pretty much without bounds until your machine runs out of memory. So even if we only have 5 things in our hash table, we can store, you know, 1,000 license plates, no problem.
Nope, never mind.
Okay.
I was going to ask if there was, I guess that's what I'm asking. Will there be any conflicts with the hash function and the hash table size? Like, is the function set up in such a way that we won't get continuously looping hashes, like, you know, setting up a hash size to be a prime number eliminates that kind of looping?
So that's a important concern when we do probing, because with probing we keep rehashing and we keep trying different locations in the hash table, and we worry about things like, you know, a prime length of the table, so that, you know, we try all the locations before we come back to the first one. But we're not doing probing in here, we're doing chaining. So your hash function is just taking in the key, the license plate, giving you back an index, and that index is guaranteed to be between 0 and hash table size minus 1. And it points you to that location in the hash table, and you're done. You're done with the hash function. Now you just use that linked list, and you basically do like a linked list PA1 assignment. Store stuff in there, look for stuff in there, and so on. So yeah, that question is really kind of the key difference between probing and chaining. Alright, so remember, everything that we're doing in here is dynamic memory. So the hash table is declared as just a pointer because we don't know how big it has to be to begin with. So we allocate space for the hash table dynamically. Since we're allocating it dynamically, each of these is a hash entry, but it's not pointing to any particular location in memory. And so how could I set up, you know, hash table bracket 0? How could I initialize this to point to an actual struct node instead of, you know, just pointing to null where I'm going to segfault or something? How do I give this a reasonable value? Any ideas? If I don't do something, first time I try to work with this node, it's going to be null. I'm going to get a segfault. So I've already set this up to say it is a pointer to a struct node. And I know that struct node should be a sentinel on a linked list. Is there something I could do to actually give it a particular value? And let me remind you what some of your functions are. Yeah, go ahead. Take a shot.
You mentioned the functions. I was looking at the functions. I was going to suggest something like, you know, the size of the of each hash entry, right?
Mm-hmm.
So you could say that the address of that is equal to the address of a sentinel plus the size of the hash entry.
Okay. So you could do a malloc, in other words, with the appropriate size for a hash entry. And that's effectively what we want to have happen. But there's a less labor-intensive way to write this statement. Because malloc, we got to call malloc, we got to have standard lib, we got to figure out how many things to put in here, we got to do size of and all of that. But the listinit function creates an empty linked list and returns a pointer to the sentinel node. That's PA1, right? In your main program, when you wanted a linked list, you said, you know, my list equals whatever we called the init function in PA1. Here it's called listinit. So in fact, if I just said hashTable bracket 0 equals listinit, that takes care of everything. It allocates memory. It might set the data fields equal to some, you know, tags so that we can recognize it. Set the plate first name, last name to something distinctive. It sets the next field to null. It returns a pointer to that sentinel node. And here I say set hashTable 0 equal to that pointer. So my initialization of the hash table is a call to malloc, and then just setting, you know, hashTable bracket I equal to listinit for I equals 0 to n minus 1. So make yourself a for loop, and inside that loop, set each element of the hash table equal to what you get when you call listinit. Every time you call listinit, it returns a different value. Because what it does is it creates, you know, a rectangle somewhere in memory with a plate, a first name, a last name, and a pointer. And this will say, you know, okay, so hash entry 0 points here. The next time you call listinit, it makes a new rectangle, plate, first name, last name, and a pointer. And if I is equal to 1, it'll set hash entry 1 to point to that. And when you're done, you've got 100 sentinel nodes in memory just waiting to be used. All right. Chat question. Primary purpose of the hash function is to get us from, for PA3.
That's an exam question.
Sorry. Oh no, related to PA3. Is to get us from you know, our license plate, which is a string, to an integer index, which we can use for an actual array, which is indexed with consecutive integers starting from 0. So the hash function basically lets us say, you know, I want to store ABC123, and it tells us, okay, store that, you know, right here. And for PA3, it's basically telling us which of our, say, 100 linked lists we should store our information in. All right, let's go one level deeper here, and let's think about the nodes of the linked list. And you've got a structure for it up here in the beginning. A node consists of a plate, first name, last name, and a pointer to the next node. And so let me copy that over. Now, in our previous assignments, our data was just called data, and it was just an integer. But in this assignment, we have 3 pieces of data, and instead of being integers, they're strings. But they're really pointers to characters, because that's what we mean by string in C. So let's say this is what our node looks like. And let's say we're inside our list add function. Right? So list add takes a sentinel node and then these 3 strings, the license plate, first name, and last name. And since we don't care about the order of these, your list add function should add to the beginning of the linked list. So we've got a list in memory. There's a sentinel node. And maybe it points to something else, and it points to something else, and so on. And we want to add a new node. So this is a mix of pseudocode and C, but I want to give you an idea of the kinds of steps you have to do, not necessarily the code to do those steps, but I want you to think about the different things that have to happen to create a node, because it's a fair bit more than if we just have a node with an integer value. And the reason is because of these fields here, which are pointers. They're arrays, but remember, you're not allowed to just make this an array of 256 bytes, right? That's going to cost a lot of memory. So you have to define these as character pointers, but we can't use a field like this until we allocate space for it. So let's say we want to say, add plate, first name, and last name. And we want to add those to, let's say, sentinel node. So here's our sentinel node. So we start off the same as PA1, right? So make a new node, call malloc, figure out how many bytes you need, size of struct node. Alright, so that gives us a node. New arrow next equals sentinel next. So here's our new node. This sets the next field to point to what the sentinel's pointing, and then sent next equals new. Right, so that's what we've been doing. That's your push function in PA2, for example, that squeezes this node in between the sentinel and the first node. All right, so these fields, first, last, and plate.
I have a question.
Yeah.
For making the sentinel node in PA1 and 2, we set it to the data value to just 1, 2, 3, 4, 5, 6, 7 or whatever. What are we gonna set plate first and last to in the sentinel node?
It's up to you. Technically, you don't have to set them to anything, but that will cause Valgrind to give warnings. So at the very least, you should set them equal to something, and you could just set them equal to null if you wanted. But it's
Can you set a string to null like that?
Yeah, it's a pointer, so you can set any pointer to null.
Okay.
But it may be worthwhile putting some bogus values in there that you recognize, just in case you happen to do something funny in your code and you end up pointing to the sentinel node. Instead of getting a seg fault, it would tell you, the license plate is ha ha ha, and you'll see that and say, oh, wait a minute, that's my sentinel node tag, and it might help you catch some issues. So when we want to store the license plate, let's say we've got a variable named plate. It's an argument to the list add function. We want to store that in this top field, right? Remember, this field is just a pointer to a character. So we need to allocate space for it. So we'd want to do something like new plate equals, and we're going to need the malloc. And how many bytes do we need to store this plate? So how can we figure that out? If plate's a variable, it's a character array.
How do we figure that out, you mean? Is what you said?
Yeah, how do you find how many bytes you need to store plate?
String length.
Yeah.
Of whatever it is you need.
Use the string length function. Right? String length takes the address of a string and starts counting how many characters there are until you get to the null terminator. So if plate is abc-123, string length will return 7. And there's a really important detail here, which is if you have a string whose length is 7, you actually need 8 bytes to store it in memory, because you need an extra byte for that null terminator. So in a case like this where you're dynamically allocating memory to store a string, make sure you add 1 to the string length. That is super duper important. And if you forget to do this, it's one of those bugs that 15 times out of 16 will have no effect. And 1 time out of 16, it will set up these little time bombs. And they will pop later on in your program and cause some weird error that'll be completely unrelated to this. And it will send you off on a wild goose chase, because when the program crashes, it'll be in some area of your program far from here, but this is actually where the error was set up. So this is a really painful thing to debug. And my only advice at this point is just try not to introduce this bug up front. All of this stuff with dynamic memory, debugging becomes a lot harder, and this is probably the worst bug to try to find. Because if you don't allocate space for that, that null terminator will potentially step on another field in your code. So allocate space for this, and then we can use string copy, new arrow plate, comma plate. And this actually copies the bytes from this string that was passed to the list add function, for example, into this string that you just allocated space for right here. And string copy will copy all the bytes plus the null terminator. So in the past, when we wanted to set the data field equal to n, we just said, new arrow data equals n. Here it's a little more complex. First we've got to allocate space, new arrow plate equals malloc, and then we have to string copy because these aren't just integers, they're arrays of characters. So that's the other big potential gotcha in working through that part. All right, any questions on this?
Looks good to me.
All I can say is thanks for pointing that out. I definitely would have made that mistake.
Yeah, and that's the first time you make it, you almost have no way of knowing that's what happened. You really have to be down at like the byte level looking at, every single thing in GDB. And I don't know how long I spent, the first time I did that, and I forgot the +1. I don't even remember how I found it finally, but it was a lot of frustration. But that's something, if and when you make that mistake, it'll be the only time you do it, pretty much guaranteed, because it's so painful. All right, the other thing to keep in mind is string compare. So we've got our list of nodes, and you're looking for, a variable plate, right, that was passed to like your find function or your search function, and you're looking for a node where this plate field is equal to plate. So you do the usual walk down the list. So let's say you have, a struct node pointer named current. And so in the past we used to say if current arrow data equals n. In this case we would say if current arrow plate, and we'd like to know if that's equal to the variable we're looking for. You can't do this, right? This will almost never be equal. So there's a scribbled out comment for you, right? What you got to do is you got to use string compare. So you can say something like if string compare, and you give it two strings, current arrow plate, comma, and then the plate that you're looking for, and I'm just assuming it's called plate. And to tell if these two strings are equal, see if string compare returns 0. If they do, then you know the strings are equal. And if you just try to compare this with a double equal, compile, fine. Run, fine, but it'll never be equal. Yeah, was there a question?
I just realized I ate like an entire sandwich with the mic right next to my mouth.
Oh. All right, so good on this. This should get you through the gorier aspects of manipulating the individual nodes in the linked list. And other than those details, right, the linked list code should be pretty familiar to you. List init is making the sentinel node. List add, you have to allocate space and do the string copies, but then you squeeze it in to the list right after the sentinel. List find, start with the node after the sentinel, walk the list, use string compare to check. List length is your print function from PA1, but instead of printing, tally, right? Initialize a counter, bump it up as you go through, and at the end that tells you how many nodes were in the list. List print is just like, the print program from before, except that you need to print it out in the right format. And then list free is slightly different. The main thing to remember with list free is that you don't just free the node that you allocated. You got to free those 3 character pointers too. So free, new arrow plate, new arrow first, new arrow next, and then free new. And that's how you release a single node. And then to release all the nodes in the list, that's your cleanup function from before. Just
So we need to clear next. Don't you mean last?
that's called next.
You said we need to free plate first and next.
Oh, so free plate first, last, and then free the node itself.
Okay.
Yeah. Yeah, don't free next. All right, good enough for now. Definitely work on this like a little bit at a time. Don't try to do it in large chunks. When you sit down to work on it, pick a piece. I'm going to work on the lists. I'm going to work on the hash function. I'm going to work on the hash table. I'm going to work on the main program. Pick a piece of it, right? And decide what parts of that piece you want to tackle and in what order, and start thinking it through, drawing pictures, and then writing code, and try to make progress throughout. Right? If you're working on the hash function, write a main program to test the hash function. Call it with a bunch of license plates, see what it hashes to, see if it matches the sample code. If you want to work on the list functions, write a separate main program that calls list init, calls list add, calls list print, and lets you exercise your code with that. And it's okay to write 5 different main programs that you throw away as you develop each of the pieces of your program. those are called test beds, right? And we generally have a lot of test beds for a piece of code that we're working on for a large program. All right, so let's go back to talking about trees. This is what we started on Monday, or on Friday actually. Not Friday, last Wednesday. So we talked about the basic ideas of trees. We talked about some terminology about nodes, parents, children, root, and so on. We talked about properties, the fact that there's no cycles, the fact that every node has 0, 1, or 2 children. Every node has a parent except for one node, which is called the root. And we talked about some other terminology like the depth of a node, number of steps from the root to the node, the height of a tree, which is the deepest node's depth. And we talked about binary trees where you know, limited to 2 children. A general tree you can have n children. Binary trees you have 2 children. And we designated the children left and right. And we made the observation that that within a tree, so here's a tree. If we pick any node, like C for example, right, so this whole tree, A is the root, but if we pick any node such as C, that itself is the root of another smaller tree. It's a root of a tree containing 3 nodes. B is the root of another tree containing 3 nodes. And in fact, G is actually the root of a really, really simple tree. A tree containing a single node, which is just the root, G. And so even though we see this whole thing as one tree, we can also view it as a collection of subtrees. And the idea of a subtree is more than just a piece of terminology. It's a really central idea to how we're going to manage and process data stored in trees. And so if we think of this tree with a root A, we could describe the left and right subtrees of A. This would be the left subtree, and this would be the right subtree. So the left subtree is the tree whose root is A's left child, and the right subtree is the tree whose root is A's right child. And this has a pair of subtrees. One of them is F, and one of them is G. And G itself has a left subtree that is null. It's a tree containing 0 nodes. Right? Can you see it? It's right there. And G also has a right subtree that is null. And if somebody starts talking to you about, you know, trees are really just made of other trees, you should look a little suspiciously at them and be prepared for them to start talking about something called recursion. And recursion is probably the biggest takeaway from this course. Other than, you know, learning how to make hierarchies of functions, the biggest sort of technical takeaway is recursion. And recursion really sets us up for all the advanced stuff. Sorry, say again?
Have you looked up recursion on Google?
I can imagine, like C recursion maybe?
Yeah, exactly.
Cool.
Did you mean recursion?
Yeah. Yeah, so the joke is the secret to understanding recursion is to understand recursion. That'll make sense later if it doesn't make sense now. So what is this? It's the idea that sometimes, you know, if we want to understand a tree, well, it's pretty easy to understand this tree. It's a thing with, you know, this tree on the left and this tree on the right and this thing at the root. That's all you need to know, right? Except, what is a tree? When I say this tree on the left, how do I understand this tree? Well, you know, it's just a thing that has a tree on the left and a tree on the right and a root. And this can sound like, you know, bad humor in a comedy club, but this is actually how we're going to be able to do programming and do analysis and come up with algorithms to do all kinds of manipulations on trees. And it generally feels kind of weird at first. It kind of feels like we're cheating or something. But once we get into this mindset and we start looking at problems recursively, we suddenly find we have this like totally new powerful tool for revisualizing complex problems. And so let's do a coding example, because I've been talking for an hour and I'm getting tired of hearing myself. I don't know about you. So let's do some code. So we talk a lot in 215 about adding up integers, right? So let's write a function to add up the first n integers. And I'm going to call this function sum of n, and this function will return 1 plus 2 plus 3 plus dot 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 plus n. All right. It's going to be a simple for loop that just adds up the first n integers. And my main program is just going to be a loop from 0 to 10, and this is just going to say the sum of the first, %d integers is %d. And I'm going to print out I, and I'm going to print out sum of I. So this is my test bed, right? This is my sample main program I'm going to use to exercise this sum function. Alright, so I'm going to call this total, right? Total equals 0. And so this is probably a reasonable attempt at the program, right? My function sum has a running sum, right? These are always your best friend. Running sum initialized to 0, and then I take all the integers from 0 up through n, including n. I probably could have started at 1 if I wanted. And I just add each of those integers to total, and then I return that sum. So let's compile that and let's run it. And this is not, terribly mind-blowing. The sum of the first 5 integers is 15. 1 plus 2 plus 3 plus 4 plus 5. So this is very straightforward, right? And the way we wrote this function was to use what we call iteration. Iteration means for loops, basically. But there's a very different way we could write this same function. And it comes down to this idea. We've touched on this in 215 this quarter. We did this in detail last quarter in 215. We haven't gotten there yet this quarter. But there's this idea that we can redefine this function as follows. If n is equal to 0, this function sum should just return 0. Sum of the first 0 integers is 0. Otherwise, we could write this without a loop as being n plus the sum of the first n minus 1 integers. And in 215, we call this a recursive definition. So I'm defining n, the sum of n, to be the sum of the first n minus 1 integers plus n. Because this is 1 plus 2 plus dot 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 plus n minus 1 plus n. Well, that's this. And if I don't have this case up here, this will just keep, sum of 1 will be 1 plus sum of 0. Sum of 0 will be 0 plus sum of minus 1. sum of minus 1 would be minus 1 plus sum of minus 2, but it's never going to actually get an answer. It's going to keep saying, you know, well, okay, I need to find the sum of minus 2, and to do that, it'll say, well, I need the sum of minus 3. So this stops us from you know, deferring forever. It gets us to a point where when we ask for the sum of 0, we say, oh, okay, that's just 0. So these 2 lines in my definition, I can turn into 2 lines of code in my function. So I'm going to get rid of all of this. And I'm going to code this first line. Sum of n equals 0 if n equals 0. So I'm going to say if n equals 0, return 0. That's just that first part of that recursive definition. And the other part is, you know, my sum should be n plus sum of n minus 1. And so we can write that like this. Return n plus sum of n minus 1. And if we compile that and run that, that works perfectly well too. So this is a recursive function. It's recursive because the definition of sum involves calling the function sum. All right, questions about this? If you haven't encountered this, this should be looking pretty strange.
So that runs itself. Okay, yeah, I see it.
Okay.
It's an interesting way to do recursion.
Yeah.
Because I've done a lot of recursion before, but I've never done it in such a way that it actually returns things when it's done.
Mm-hmm. Cool. So this is really different, and typically when you start working with recursion and recursive functions like this, your brain will go through a lot of kind of angst / delight. Sometimes it will look like this makes no sense, and sometimes it'll flash and be crystal clear. It's like, I get it, you know. And then maybe you'll try to explain it to your friend and it'll run away. It takes some getting used to. And so if it makes perfect sense to you, that's great. If it confuses the heck out of you, that's great too. So we're going to work with this for the rest of the course. We're going to be using recursion to do a lot of things. And we're going to begin that process by looking at things we do to trees. And it comes out of this idea that a big tree is just a bunch of little trees put together by attaching them to a root. And so we can talk about properties of trees in terms of properties of subtrees. Well, subtrees are just trees. So yeah, we can do this like the same thing with Fibonacci series. So and that's a 215 subject we haven't gotten to yet in winter. But you know, the nth Fibonacci number is the n minus first Fibonacci number plus the n minus second Fibonacci number. And so we could write a Fibonacci function. So here's let me change this. And let's just print out the first 50 Fibonacci numbers. So fib of %d equals, and we'll just call our fib function. And so there's got to be this base case for this, because, you know, if I want to know what f of 1 is, I can't just say it's f of 0 plus f of minus 1. There is no minus first Fibonacci number. So we're going to define f of 0 equals 1 and f of 1 equals 1. And then this formula will be for n bigger than or equal to 2. So let's recode our function like this. So if n equals 0, we'll return 1. If n is equal to 1, we'll return 1. I could have done an OR statement, or less than or equal to. Otherwise, I'm going to return fib of n minus 1 plus fib of n minus 2. And that's my whole Fibonacci function. And if you tried to code this by hand in the past, it's not impossible, but you do have to keep track of the previous number and the previous number, and you have to move those along and so on. And it takes a little bit of care and a bit of thinking. And this, you don't even have to think about this if you have this definition. Fn is Fn minus 1 plus Fn minus 2. Well, I just copy that into C code. Let's just take f fib n minus 1, fib n minus 2, add them together, and return that for fib n. But let's not make typos.
Your print statement needs a semicolon.
That too, thank you. Alright, ready? Here we go. So this is great. These are the first few Fibonacci numbers, 2, 3, 5, 8, 13. We got rabbit populations or flower petal counts here. But check this out, right? What's going on here? This is slightly horrifying, right? The 45th Fibonacci number, well, just add these two together, and you should get fib 45. Why is it taking my laptop, 15 seconds to add those two numbers together?
Because it's actually adding every single one up to it.
Yeah.
Every time it does it.
So this is a downside to recursion. It can be really slow. It can also be really expensive in terms of memory and other computer resources. So we're not going to worry about this too much right now. This turned negative because we overflowed 2 billion. But the point is, right, we could write this function simply from the definition of what this Fibonacci function is. The nth term in the series is the sum of the two previous terms. Well, that translates directly into here. All right, so how do we tie this into trees? Let's take a look at a first operation that we want to do with trees, which is traversal. Traversing a tree means moving through the tree and typically printing every element in the tree. So let's put our favorite tree up. So there's a binary tree. And if I want to print the contents of this tree, right, I know what the root is. Remember, our handle to the tree points to the root. So I can print out the root node's data. That's just like, root arrow data. I could certainly print the 20. This would be something like, root arrow left arrow data. This is root arrow data. And I can print the right subtree's root node as just root arrow right arrow data. But now I got a problem, right? After I've printed this node and this node, well, I've got 4 nodes I have to print now. I have to do, root arrow left arrow data, root arrow left arrow right data, and so on. And the further down I go, the more different, branches I'm going to have to follow. And so we can do this, but it involves a fair amount of housekeeping, and it's also going to require the use of a stack. And we're probably tired of stacks at this point from PA2, so we don't want to do that. But there's a totally different way we can describe the problem of printing all the stuff in a tree. And it works like this. If we want to print the root value of a tree, right, that's easy. We just print root arrow data. That's always, you know, a slam dunk. If you have a tree, that's one node we can print without any work. We can just say print the root node. And so let's make, you know, a function called tree print. And let's pass it the root of a tree. And I can say print root arrow data. That's easy. But then I got all these other nodes I have to print. But I can look at this as two additional problems. The first problem is to print everything in this subtree. And the second problem is to print everything in this subtree. How do I print all the data in this left subtree? Well, this subtree is a tree whose root is root arrow left. How am I going to print it? I'm going to use this amazing function I heard about called tprint. And I'm going to say, hey, just print stuff that's in the left tree. And then I'm going to use that same function one more time and say, hey, let's print all the stuff that's in the right subtree. All right, so here's the leap of faith. If I believe that this tprint function works, in other words, if this function prints the entire tree whose root is given as its argument, if I really believe, I fix it in my brain, I go to a hypnotist, they wave the watch in front of me and they tell me this works, and I really come away believing, yes, if I pass the root of a tree to this function, it will print the entire tree. If I believe that, then I have to believe this code will print the entire tree. Because what does this code do? It prints the root node's data, it prints everything in this left subtree, it prints everything in this right subtree.
Wouldn't you get a seg fault?
We'll take care of that.
For believing.
Yes. But yes, you are right. If we don't add something in this little space up here, we will get a seg fault. But if we don't worry about it, if we just believe that, you know, magic will happen and this will print an entire tree, well, these three steps will print this entire tree. Because this clearly prints the root node's data. And this, you know, since tprint prints the contents of a tree and I'm feeding it the left subtree, this will print all of these things, and this will print all of those things. Well, that's all there is in the tree. There's the root node, there's the stuff on the left, there's the stuff on the right. And this will actually work, as long as we don't seg fault. And the seg fault happens for the same reason that if we try to do Fibonacci's by just, you know, going further and further down, or we try to do sums by going further and further down, if we don't have this base case here, we eventually start calling our function with negative numbers. And that doesn't really make sense. Well, here, you know, when we get down to the point where we're trying to print a tree containing, say, just, you know, one node like a 10, we can print the root node data, but when we try to print the left subtree is null. And if we call tprint with a root that's null, this print statement's going to seg fault. We can't dereference a null pointer. So we need an extra condition in here, which is if the root is null, return. Because if someone asks us to tprint an empty tree, we don't have to do anything. We'll say, sure, I'm done, and we'll just return. But other than that one edge case, if the root is not null, we'll print out the root node's data, and then we'll tprint the left and right tree. So this is a 4-line C function that will compile and execute perfectly. It's completely legit. And it will do that whole business of saying, okay, well, I'm going to print a 40, and I'm going to remember this stuff, but first I'm going to go off and I'm going to print a 10 and a 20 and a 30.
Was this tprint just going to run itself?
Well, so we would call this from some function. So like you'd have, this would be a function I'd write in C, and then my main program would have a tree whose root is root, and we could call, tprint root, and it'll print out all our data. Say again?
I'm saying for this tprint, if we were to make the tprint function, would it just run itself recursively a ton?
As soon as something calls it once, it will keep calling itself recursively.
Okay, yeah, that's it. Okay.
So what would this do with this tree? Let's make a 40. Let's just make a tree of letters. And we've got about 5 minutes. Let's see what this function does. So if I want to tprint this, okay, so what do I say? So here's my root. Is the root null? No. So let's print out the root data. So this is going to print out the letter A. And then I'm going to tprint root left. So I'm going to call tprint on this tree. And then I'm going to call tprint on this tree. Right, the right subtree. And then my tprint's going to exit. So when I call tprint on this original tree, first it's going to print an A, so this is my output. And then it's going to tprint this, and it's going to tprint that. Alright, what happens when I call tprint on this? First it's going to print out the root node, so B is going to appear on my output. And then it's going to say tprint this tree, and then tprint this tree. So I call tprint on a tree whose root node is D. It's going to print out a D. And then it's going to call tprint on the left subtree, which is null. And then it's going to call tprint on the right subtree. Alright, it calls tprint on null, it returns. It calls tprint on null, it returns. So now it's done calling tprint on D. The next thing it's going to do is call tprint on E. And same thing, it's going to print out the root node's value. It's going to call tprint on null for the left subtree and the right subtree. Those aren't going to print anything. So when it comes back from my call to tprint on this tree, this is what's been printed. My original call to tprint the root, checked to see if it was null, it wasn't, it printed the root node's data. Now it's printed the left subtree, BDE. And now it's got one step left, which is to tprint this. And you can go through the same exercise on paper. First it's going to do a tprint on C, which is going to do an output of C, a tprint of null, and a tprint of null. And then it'll try to tprint the right child, G, which will print out a G, and it will tprint null and null, and be done with that. Oh, I skipped a step. I'm trying to finish in 2 minutes. It'll print out C, and then it'll tprint F, and it'll tprint G. And then you go through into tprint F. First we print out an F, and then they tprint the two nulls. And then we come back here and we tprint G, and we tprint the two nulls. That completes the tprint of this subtree. And now back in our original algorithm, we printed the root, tprinted the left, tprinted the right. We're done. And this is what tprint output when we called it on this tree. And it printed all 7 nodes. Alright, so that's a first look at how we're going to use recursion with binary trees. And we're going to do this again and again with lots of different functions and lots of different algorithms. So we're going to get a lot of practice at this before we start coding it. Your 4th programming assignment will be related to binary search trees. But we're going to have, another week of lecture before PA3 gets turned in. So we'll have at least, a week and a half of lecture before you have to start coding PA4. So we're going to get a lot of practice with this. and we'll be talking about it a lot over the next few classes. All right, we are out of time, so I'm going to call it quits there. Have a good afternoon. If you're in 215, try to do something to clear your head maybe, and relax for that exam, and I will see you there. Otherwise, have a good afternoon, and I'll see you either in office hours or next week. All right, thank you. Bye.
Thank you. See you in an hour.
See ya.